Hi, everyone. Welcome to our last seminar talk for the spring semester. We're very happy to have Herman Chau from the University of Washington to talk about enumerating higher Bruhat orders through deletion and contraction. All right.
Well, thank you so much for the invitation. Yeah, I'm here to talk about the higher Bruhat orders and then specifically using deletion and contraction to enumerate them. So I'll just first give a couple related areas as some motivation for why people care about the higher Bruhat orders. So they originated from this paper by Manin and Schechtman in 1989. And in that paper, they talked about these specific hyperplane arrangements called discriminantal arrangements, which generalize the braid arrangements. And then they looked at paths from opposite points that cross through the hyperplanes and consider the topology. So that's kind of where it started. There's connections to alternating matroids, pseudo-line arrangements, rhombic tilings, and we'll actually get more into the rhombic tilings later in this talk. Something called maximal weakly separated set systems, and then also some connections to cohomology, specifically Steenrod operations. So this is just kind of a very brief overview that there are lots of connections to other areas. And then let me now dive in to some of the motivating background. So we'll start off with something probably people are more familiar with, which is the weak Bruhat order on the symmetric group Sn. I'll use sigma I to denote the adjacent transposition where we just swap the numbers I and I plus 1. And W naught will denote the longest permutation, so the one that flips all the numbers from 1 through n. So our definition of inversion will be Ij is an inversion if I is less than j, but W inverse of I is greater than W inverse of j. So this is like inversion on the values, not the positions. And then a reduced expression for permutation W is going to be some way of decomposing W into adjacent transpositions, and then doing it in a way of minimal length. So in particular, the length of this expression is going to be the number of inversions of W. And then I might also just omit the sigmas and just write the indices. And in that case, we'll call it a reduced word. Okay, so as an example, just in S4, in this case, W naught, if you write it in two-line notation, at the top you have 1 to n, so 1 to 4 in this case. And then on the bottom, you have W of 1, W of 2, and so on. You can also drop the first line and just write in one-line notation. And then at the bottom, here's an example reduced expression. So if we want, we can also omit the sigmas and just write it as 1, 2, 3, 1, 2, 1. So the weak Bruhat order is a partial order where we have, if you compare two permutations V and W, you look at reduced words for V and look at reduced words for W. And if some reduced word for W has as a prefix a reduced word for V, then we say V is less than or equal to W. So specifically, this is the right weak Bruhat order because a way you can think of it is you start with a reduced word for V, and then you can multiply by adjacent transpositions on the right to get to a reduced word for W. And another way to think about the weak Bruhat order is you look at certain cover relations where you look at the inversions in W, and if it's obtained from the inversions of V just by including one more inversion, Ij, then you have a cover relation in this weak order. So as an example for S3, I've written out here 3 different ways to represent the weak order. So on the left, we just have the ordinary permutations. 1, 2, 3 is at the bottom, and 3, 2, 1 is at the top. And kind of at each step, you can see we're multiplying by a specific adjacent transposition. So in the center, I wrote down the possible reduced words for each of these permutations. And then on the right, I wrote down the inversion sets. And I omitted like the parentheses and commas, just so it like fits on the page. So the topmost permutation 3, 2, 1 has all the possible inversions. And you can see at each step, each adjacent transposition we're multiplying onto it increases the inversion set by throwing in one new inversion. Cool. So that was the weak partial order. And then I want to dive in now more into reduced expressions. Specifically, you can represent them using things called wiring diagrams. So this is for the reduced expression sigma 1, sigma 2, sigma 3. sigma 1, sigma 2, sigma 1. On the left, I just write the numbers 1 through n. And then on the right, we have the corresponding permutation. So here the number, you can think of it as 1 is going sent up to the last position. And if we draw in color lines for everything else, you can kind of use the wiring diagrams to track where each number in the original permutation goes. Equivalently, we don't have to write the sigmas. We might also keep track of which inversions are being introduced at each crossing. So at the first one, let me kind of like flip back and forth here. The sigma 1 in this reduced expression corresponds to introducing the inversion 1, 2 to start with. And then the sigma 2 corresponds to introducing the inversion 1, 3. And then we introduce the inversion 1, 4, 2, 3, 2, 4, 3, 4. And so this is another way to think about a reduced expression, and specifically for a reduced expression for the longest permutation W0 in S4. Cool, so if we start with a reduced expression, we can also do some operations to obtain other reduced expressions. So the two possible things we can do are called commutation and braid relations. So the commutation relations are pretty simple. It's if we're looking at a sigma I and a sigma j, where I and j differ by more than 1, then we can just swap their order. So this is in the previous example, if we look at the 1, 4 and the 2, 3, those wires don't involve, like, they are disjoint pairs of wires, and so one could in principle swap their order, and it wouldn't really affect the reduced expression. The braid moves are something a little more complicated. It's where you see a sigma I plus 1, sigma I, and you can replace that with a sigma I plus 1, sigma I plus 1. So the braid relation also gives you back a reduced expression for the same permutation W. So as an example, if we started off with our reduced expression sigma 1, 2, 3, 1, 2, 1, we could swap the sigma 3 and sigma 1 in the middle to get sigma 1 and sigma 3 instead. Or we could also do a braid relation at the end where we had a sigma 1, sigma 2, sigma 1, and then you replace it with a sigma 2, sigma 1, sigma 2. So by using commutations and braid relations, we can start off with a reduced expression for some permutation and possibly get many other reduced expressions. So if we visualize this again with wiring diagrams, so at the top is the one we had seen on a couple slides ago. And I had mentioned they involve disjoint wires crossing. So one could just like commute the sigma 3 and the sigma 1. On the other hand, to perform the braid move, you're looking for crossings that are adjacent to each other. So sigma 1, sigma 2, sigma 1. And it kind of looks like you're doing some sort of flip on those specific crossings. Now, there's a nice theorem from Matsumoto and Tietz, which actually says that all the reduced expressions can be obtained in this way. Specifically, if I look at the set of reduced expressions for W, any two of them are connected by some sequence of commutation and braid relations. So this is true for any W in Sn, but actually for this talk, we'll only care about the longest permutation W0. So what I can do is I can actually write down all the reduced expressions for our permutation 4, 3, 2, 1. And here I've drawn out edges connecting reduced expressions, well, reduced words, because I've omitted the sigmas. I've drawn out edges connecting them if they have a braid or commutation relation that goes from one to the other. And specifically, the red edges, those correspond to commutation relations, and the black edges correspond to the braid relations. We'll say that two reduced expressions, row 1 and row 2, are commutation equivalent if they differ just by a series of commutation relations. So if I go back to this graph, the two reduced expressions on the bottom, 1, 2, 1, 3, 2, 1, and 1, 2, 3, 1, 2, 1, those are commutation equivalent. Everything in the red diamond on the left is also commutation equivalent. Same with the red diamond on the right. And then same with the two reduced words on the top. So what we can do is we can actually consider commutation classes and obtain a new graph by contracting these commutation edges. So if we did that, what we obtain is the simpler graph here. And this will actually end up being the second higher Bruhat order. So the higher Bruhat order is generalized the weak order. And in the case of the second one, it is looking at these commutation classes of reduced expressions. And just for one more time, we can like visualize this on the wiring diagrams. So here we have two commutation equivalent reduced expressions. And since sort of like these two crossings involve disjoint wires, you could also represent it just by putting them on the same so that those two crossings line up. Okay, so with those as kind of the motivating examples, I'll now dive into defining the higher Bruhat orders. So as I mentioned, the first one is the weak order on Sn, and the second higher Bruhat order is a partial order that you can put on these commutation classes. And something to notice is that if you look at Bn1, the elements in there are permutations. So you can think of them as total orderings on bracket n choose 1. And bracket n is just the numbers from the set 1 through n. So bracket 1 choose 1 are like the singleton sets. And then Bn2, we saw that they corresponded to reduced expressions. And we could have looked at kind of the order of the inversions that were added. So in a way, the elements in there are total orderings on bracket n choose 2. So it's an ordering on how we add the inversions. The partial order, in the case of the weak order, they're generated by adding in adjacent transpositions. And in the case of the second higher Bruhat order, Bn2, they're added by doing braid moves one at a time. So there's an analogy there where transpositions are flipping two elements, and braid moves, we'll see later, you can also think of as doing a flip. Okay, so we'll need some definitions to fully define the higher Bruhat orders. So the first thing I want to introduce is something called a packet. So here we start off with some subsets x1 through xk. And I should mention, we're assuming here that all our k subsets, they're ordered in increasing order. So x1 is less than x2 is less than xk. And then the packet of x is obtained by considering every possible k minus 1 subset. So big X sub k is where you delete the kth element, and so on. So the lex order on the packet is going to be xk through x1, because in xk you delete the largest element, so that corresponds to the lexicographically first element in the packet. And then the anti-lex order is just the reverse. So we can talk about how sets of size k commute. They're going to commute if their packets turn out to have empty intersection. So another way to think about this is if two sets don't have enough overlapping elements, if their intersection is not size k minus 1, then they'll be able to commute. So as an example, if we look at the case where n equals 5 and k equals 3, here are a couple sets of size 3. So we have x is 1, 2, 3, y is 1, 3, 4, and z is 3, 4, 5. The packet of x is obtained where I delete the last element, the middle element, and then the first element. So the packet of x is 1, 2, 1, 3, and 2, 3. The packet of y is 1, 3, 1, 4, 3, 4, and the packet of z is 3, 4, 3, 5, 4, 5. So I've highlighted in red and blue like these overlapping elements in the packets. And so from this, we can see that x and y don't commute because their packets both contain the element 1, 3. And then y and z also do not commute because their packets contain the element 3, 4. But I did want to point out that like not commuting is not a transitive relation. So x and z do commute, even though x and y don't commute, and y and z don't commute. Okay, so the main object we'll consider for the hybrid Bruhat orders is something called admissible orders. So an admissible order is a total order on the k subsets of bracket n. But we have this additional restriction. So if we take our total order rho and restrict it to any packet p of x, it needs to order the packet in either lex order or anti-lex order. So with this restriction, a and k, this will denote the set of admissible orders on bracket n choose k. And for a given admissible order, we can define its reversal set. So this is kind of like an analogy with the inversion set of a permutation. These are the sets x, where if you restrict to the packet p of x, then you get the anti-lex order. And we'll say rho and rho prime differ by commutation if all we do is we transpose two commuting sets, x and y, inside that total order. And now we also have packet flips, which correspond to kind of braid moves. A packet flip is if p of x occurs as a saturated chain, so we see like xk, xk minus 1, all the way to x1 in a contiguous fashion, then we can actually reverse the order, put it from lex to anti-lex, or vice versa, and that's called a packet flip. So probably easiest to just like see an example. So here k equals 2, so we're kind of back in the commutation classes of reduced expressions case. So rho 1 is the lex order on these size 2 subsets. Rho 2 we obtain by commuting 1, 4, and 2, 3 because they don't share any elements and their packets have empty intersection. And then rho 1 and rho 3, they're obtained by flipping the packet p of 2, 3, 4. So I'm not sure if my mouse is visible, but if you look at the last three elements here, 2, 3, 2, 4, 3, 4, they get flipped in rho 3. And so that's analogous to doing the braid move on the last three crossings in our wiring diagram that we saw earlier. Cool. So I'm going to define one more set before we get to the actual partial orders. So there's an alternative definition of the higher Bruhat orders that involves certain subsets as opposed to total orderings. So a subset of the bracket n choose k is consistent if I intersect p of x is a prefix or suffix of the packet. And when I say prefix or suffix, I mean prefix or suffix in lex order. I think there was a chat like question, but I can't quite see it. Cool. I guess I'll just keep moving.
Yeah, well, I mean, the comment is saying that it is visible.
Oh, okay, great. Cool. So there's a lemma by Ziegler which says that if I start with an admissible order and I look at the reversal set, so remember these are the sets X where the packet appears in anti-lex order, then that actually gives me a consistent subset. So as an example, if I look, this is in n equals 4. If I look at the subset 1, 2, 3, 1, 2, 4, or I look at the subset 1, 2, 4, 1, 3, 4, 2, 3, 4, these are both consistent because I would intersect it with a packet of 1, 2, 3, 4. And so the first subset here, this is a prefix of the packet of 1, 2, 3, 4. And this second packet, or this second subset, is a suffix of the packet 1, 2, 3, 4. And here was, again, one of our admissible orders. If we look at its reversal set, the only packet that appears in anti-lex order is this packet 2, 3, 4, because 3, 4, 2, 4, 2, 3 is in anti-lex order. And we can see that that set is also a consistent set. Okay, so with all the technical definitions out of the way, we can finally define what the higher Bruhat order is. So the higher Bruhat order, denoted B and K, is we take the admissible orders A and K, we quotient out by commutation equivalence, and then we give it the cover relation where bracket rho is covered by bracket sigma if some rho prime and some sigma prime differ by a packet flip where you go from lex to anti-lex. So I think the analogy to keep in mind is with the k equals 2 case, where we had the contracted reduced expression graph. And then all of the edge, you should think of all of the edges in that graph as pointing from the lex to anti-lex case. And then that gives you the partial order. So the equivalent definition is you can define the higher Bruhat order as this set C n k plus 1, which are the consistent subsets. But instead, you consider the partial ordering as I is covered by J, if J is exactly the set I, but you throw in one additional set X. So this is also an analogy with just the usual weak order, which you can think of as inversion sets with the partial order being this kind of inclusion. And it's a theorem by Ziegler that actually these two definitions are equivalent. So if I start off with some commutation class of admissible orders, and I map it to its reversal sets, then it gives us a poset isomorphism between B and K and C and K plus 1. So to illustrate, here is B42 on the left, and then C43. So B42, these are admissible orders on the size 2 subsets. And then C43, these are consistent sets where each subset is of size 3. So here I'm going to draw out kind of doing some packet flips. So for example, going up the left, we do a packet flip of the packet 1, 2, 3. And you can see that in the consistent subset case, what we did is we added the subset 1, 2, 3. And we can continue packet flipping 1, 2, 4. And we add in the subset 1, 2, 4. We add in the subset 1, 3, 4. And then we add in the final subset 2, 3, 4. Cool. So a nice property of the higher Bruhat orders is that they are a ranked poset. Specifically, it has the rank function where if you give me an admissible order, the rank is just the number of elements in its reversal sets. I'm just going to go back to the page here. If you just look at the admissible orders, it's a little hard to tell the rank. But if you look at the consistent subsets, the rank 0 element is just the empty set. And then it's ranked simply by the size of these sets. And the lex order is going to be the unique minimal element. And then the anti-lex order is going to be the unique maximal element. Since the anti-lex order has maximal reversal sets, and the lex order has the empty reversal set. So some questions like you might ask about partial orders are, what nice properties do they have? Like, for example, are the higher Bruhat orders lattices? It turns out it's not a lattice. And in fact, just computationally, you can check at B62. This is kind of the smallest example where it's not a lattice. B62 is already fairly large. I think it's 908 elements. So it's hard to draw out to exactly see that it's not a lattice. But you can computationally check that these two elements turn out to not have a join. There's like 2 elements that cover both of them. But what is true is that, well, we know the weak order is a lattice, but also if you let n and k, if you let their gap be at most 3, it turns out that poset is also a lattice. Another question you might ask about partial orders are like computing the Mobius function. So for the weak order, we know the Mobius function takes values -1, 0, 1. But there's also a theorem by McConville which says that in Bn2, if I look at open intervals and look at the order complex, it's going to be homotopy equivalent to a sphere or is contractible. And the Mobius function is related to like the reduced Euler characteristic of the order complex of these intervals. And so if it's equivalent to a sphere or is contractible, we know that the Mobius function will also take on values -1, 0, and 1. And the precise characterization of when it takes on each value is also known, but the exact conditions are a little technical. I've done some computations just like running by a computer and saw that for higher Bruhat orders beyond k equals 2, it still seems to take on values -1, 0, and 1. But as far as I know, it's not known whether or not this is the case for the higher Bruhat orders. Okay, so that was kind of an introduction to all the definitions and some of the poset properties. So now I want to start digging into the enumeration of these partial orders. So there's a very nice theorem by Stanley from 1984, which counts the admissible orders. So this is before we quotient out by commutation classes, specifically looking at AN2. So these are just the reduced expressions, but where you count commutation equivalent ones as distinct. In that case, the number is really nice. It factorizes, and it turns out to be the number of standard Young tableau of this staircase shape, n-1, n-2, all the way down to 1. And that you can compute using the hook length formula. So a natural question to ask is, what happens if we mod out by commutation equivalence? Is there still going to be some nice closed formula? Surprisingly, this is still open. And Bn2 also grows very quickly with respect to n. So it's actually hard to get data to kind of like look at these values. So as an example, as like the first few of these, from 2 to 8, these are the first values of the size of Bn2. What we could do is just look at a factorization. Because in the case of AN2, the numbers kind of factorize nicely into relatively small factors. But here, the prime factors are quite large with respect to n. So it seems unlikely that there is going to be a product formula for the size of Bn2. On the other hand, what's kind of surprising is like there seem to be relatively large powers of 2 here. And so a theorem I've shown is that actually, if you let 2 to the a be the largest power of 2 dividing n, then you can actually divide the size of Bn2 by 2 to the a plus 1. So for this holds starting from n equals 3. So for example, at n equals 8, 8 divides 8, but 16 divides b of 8 too. So to prove this divisibility property, one key ingredient is this bijection with rhombic tilings. So there's in Elnitsky's thesis, he shows that the elements of Bn2, they are specifically in bijection with rhombic tilings of a regular 2n-gon. And I just wanted to remind us that, so Bn1 is a weak order, but Bn2, they're the commutation classes of reduced expressions for the longest permutation W0. So here I just want to illustrate the bijection. We'll start with the rhombic tiling and then go to a specific commutation class of reduced expressions. So here n is equal to 4, so I have a rhombic tiling of the octagon. And I've colored in all the edges that are parallel to each other. So what we'll do is we'll start labeling the left-hand side with 1, 2, 3, 4. And then we'll draw lines connecting the midpoints of the edges that are colored the same. So here I have a line going through all of the red lines, and then it ends up on the opposite side, and I label the opposite red edge with a 1. So I can do this with all of my colored edges. And essentially what we did is we took each rhombus in our tiling, and we connected all of its opposite midpoints. So once we do this, we focus on these internal lines that we drew. And this is now very reminiscent of our wiring diagrams. You can kind of straighten it out a little bit, and you'll get exactly the wiring diagram that we had seen earlier. And this, in general, will give us a bijection where every rhombic tiling on the left, you can repeat this procedure and obtain a wiring diagram on the right. And Elnitsky showed that this is in fact injective, like different wiring diagrams give rise to different tilings give rise to different wiring diagrams, and that every wiring diagram can be achieved this way. Cool. So if we go back to looking at this divisibility property, then the proof roughly follows like this. We're going to count the rhombic tilings instead of counting Bn2 directly. And rhombic tilings can be acted on really nicely by rotation. So Z2n, this will be the cyclic group with some generator Z that acts by rotation. And the thing to note is that rotating by 180 degrees yields a distinct tiling. Sort of if you look at any tiling of the 2n gun and color the edges, you'll notice that each possible type of rhombus appears exactly once. So there's one rhombus with edges colored red and pink, one with edges colored red and blue, and so on. And when you do a 180-degree rotation, kind of a rhombus gets sent to a rhombus of the same coloring, but on the opposite position. So you do get a distinct tiling. So what this tells us is that actually the stabilizer of each of our orbits under this rotation action, it's generated by z to the r, where r does not divide n, because we know that z to the n does not take our tiling back to itself. And so r is going to be the size of each orbit, and you can check that then 2 to the a plus 1 will divide r. So we get this divisibility property on every orbit, and hence on the entire set Bn2. Cool, so now I want to move on to defining some new operations, which are deletion and contraction, which will give us more tools to look at the enumeration, specifically looking at the asymptotics of the higher Bruhat orders. So both deletion and contraction here are defined in analogy with deletion and contraction for matroids. So the first thing is for a subset of size k. The deletion is we're going to look at the deletion specifically where we delete the element n is we look at all the subsets that don't contain n. So we intersect with bracket n minus 1, choose k. And then the contraction is, again, we're just contracting by the element n. We're looking, in this case, at all the subsets x inside of I that contain n, and then we remove the value n from it. We can now also do deletion and contraction on total orders. So if I take a total order row on bracket n choose k, the deletion is where I just consider the total order restricted to bracket n minus 1 choose k. So it's, again, we ignore everything that contains n. And then the contraction is a similar operation where we look at the total order on bracket n minus 1 choose k minus 1. We basically restrict to all the elements that contain n and then delete the value n from them to obtain the contraction row contract n. Okay, so as an example, here I have a admissible order in A42, and I let the set I be the reversal set of row, which is 1, 2, 3, 1, 2, 4. Then to delete the element 4, I look at all the elements in row that don't contain 4 and just restrict to them. So it's 2, 3, 1, 3, 1, 2. And then to contract by 4, I look at the elements that do contain 4. So 2, 4, 1, 4, 3, 4. And then I remove the element 4 from them. So that gives me 2, 1, 3. The deletion of the subset of the set I is I just delete all the subsets that contain 4. So I delete the 1, 2, 4. And that leaves me with 1, 2, 3. And then the contraction is I take all the elements that contain 4. So in this case, only 1, 2, 4. And then I delete it. And that gives me the contraction I contract 4. So kind of a nice dilemma that we have is if I start off with an admissible order, then both the deletion and the contraction are going to be admissible orders. And it preserves the commutation classes. And furthermore, if we look at reversal sets, you can delete by n or contract by n and then take the reversal sets. And that would be the same thing as taking the reversal set and then deleting or contracting by n. And similarly, if you start off with something that's consistent, after you delete n or contract n, it remains consistent. So something that's nice is that if we take consistent sets and we map it to the pair of its contraction and deletion, that's going to be an injective map. And the proof is really just that if I am given a pair, I delete n, I contract n, I can recover I pretty easily. And it's important that it lands inside the product of Cn minus 1k and Cn minus 1k minus 1. And this just follows because we saw that when you delete or contract, it remains consistent. Okay, so going into asymptotics, there's a paper by Balko that's fairly recent. And by considering the higher Bruhat orders in a slightly different context, he shows this asymptotic upper bound. So namely that if we take the log of bnk, then it's approximately bounded by n to the k times this constant, or times this 2 to the k minus 1 over k factorial. What we can do is we can improve this upper bound, pretty much getting rid of the 2 to the k minus 1. And I guess we take a log 2 in the denominator instead. So the proof for this will involve contraction and deletion, and we'll prove this refined upper bound by induction. And then I'll defer the base case until later, where we'll talk about a slightly different tool to handle the base case k equals 2. And I should mention this really holds starting at k equals 2, because when it's k equals 1, you're looking at the size of just the symmetric group. And in that case, it is not true that the log of a symmetric group, it's not bounded by n. Cool. So for the inductive step, we're going to be using that map where we send I to I delete n and I contract n. And in particular, we're using the fact that this map is injective. And we also saw earlier that that the CNKs and BNKs are isomorphic. So combining these two facts actually tells us that the size of BNK is bounded by the size of BN minus 1k times the size of Bn minus 1, k minus 1. And now we can repeat this on the Bn minus 1k part, and again split it into an upper bound of Bn minus 2k times Bn minus 2, k minus 1. So we can kind of keep repeating this. And what we'll get is that we can bound the size of Bn minus k in terms of a product of the sizes of Bi, but now we've decreased k by 1. And then if we take logs, this tells us the log of bnk is bounded by a sum of the log of, this should say bi k minus 1. So the inductive, if we then use the inductive hypothesis, along with Faulhaber's known formula for the sum of the first k powers, what we can do is we replaced that sum of log bi k minus 1 with essentially a sum of the first k minus 1 powers. And then that gives us an n to the k and a k factorial with the appropriate error on the order of n to the k minus 1. And I'll briefly mention that Balko also has a lower bound. So actually we know that if you take log of bnk, it's approximately n to the k. And we're also able to improve the lower bound from this k plus 1 to the power 4 k plus 1 to just a k plus 1 factorial times the square root 24 pi k. The proof here is fairly technical, and it's an explicit construction, so I'll just skip it, but I just wanted to mention that there's also an improvement on the lower bound. Okay, so the last thing I want to talk about now is weaving patterns. Weaving patterns will allow us to handle the k equals 2 case. So here we're going to just consider bn2, and bracket row is going to be some commutation class of reduced expressions. So the weaving pattern is going to be a function that maps each number from 1 through n to a binary string, so just a sequence of zeros and ones. And what we do is we take the wiring diagram of row, we follow each wire, and we just record whether it goes up or down. So as an example, we had our Lex ordering 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. In this case, the weaving pattern looks like this. It maps the number 1 to the binary string 0, 0, 0, and so on. And this comes from just looking at the wiring diagram. So one, if you follow the one wire, it just goes up. And for each up step, we record a 0. For the wire 2, we also follow its trajectory. And it starts off with a down step, which we record as a 1, and then 2 up steps, which are 0s. And then the same for wires 3 and 4. So one observation here is if you look at the binary string corresponding to the number I, it's going to have I minus 1 ones and n minus I zeros. But it's possible that the zeros and ones can occur in kind of an arbitrary order. And so a theorem about these weaving patterns is that this actually captures enough information to recover the original commutation class. So specifically, if I have 2 different commutation classes, they are the same if and only if the weaving patterns are the same. So this is a little surprising because it seems like we've thrown away a lot of information, but we can somehow still reconstruct the the reduced expression from just this pattern of zeros and ones. So now the upshot of this is that we can bound the size of Bn2 quite nicely. In fact, it's going to be n squared over 2 log 2 plus an error term of O of n. And the way we look at this is for each, we're going to bound Bn2 by the number of possible weaving patterns. For the value I, the number of ways you could arrange the value of the ith row in our weaving pattern is going to be a binomial coefficient, n minus 1 choose n minus I. So therefore, the maximum possible size of Bn2 is just a product of these binomial coefficients. And so we can take the logarithm of it. And so that gives us a bound on the right-hand side here. We can apply Stirling's approximation to the log of the factorials. There's also, this is a little bit hand-wavy, but we can approximate this sum on the right with an integral. And then that ends up giving us the 1/2 n squared. And I should mention there's a slight discrepancy here where I didn't write log 2s, but if you wrote log 2 everywhere, you would get a log 2 in the denominator. And in a couple of these steps, we pick up an error on the order of n. Cool, so that completes the base case and gets us started for the induction that we use contraction deletion for. Cool, so let me just quickly check the time. How much time do I have left?
You have like 10 to 15 minutes, so.
Oh, okay, cool. Then in that case, I'll talk a little bit about duality as well. I prepared some extra slides. So for a lot of the higher Bruhat orders, we can define dual notions of everything. So if we start off with a set X, before we were looking at packets, but we can also look at co-packets instead. So the packet of X we obtained by deleting elements from X. The co-packet of X, denoted P star, this is obtained by throwing in elements into X. So you consider all the elements I that you can add in that were not originally in X. And then we can define coadmissible to be total orders, where if you restrict to co-packets, it's the lex or anti-lex order. And then we can define co-consistent to be sets where if you intersect a co-packet, it's a prefix or suffix in lex or anti-lex order. So essentially we just throw the word co in front of everything, and then we have a different definition for co-packet. So if we do this, we can get something called the dual higher Bruhat orders. It's essentially the exact same definitions where we look at coadmissible orders mod out by commutation. And then instead of packet flips, we have co-packet flips. And then you can also define a C star NK to be co-consistent sets. Again, like with essentially the same definition for the partial order, which is you're adding in one additional element to get the cover relations. You can send a co-admissible order to its co-reversal set, and then that gives you a post-set isomorphism. The only thing of note is that in this case, originally it was from BNK to CNK plus 1. Here you actually step down in K, so you go get an isomorphism from B star NK to C star NK minus 1. And so the main theorem that kind of nicely connects the isomorphisms between the B's and the C's and the B stars and the C stars is that we actually get an isomorphism from BNK to B star N minus K. And then we also have an isomorphism from CNK plus 1 to C star N minus K minus 1. And we get this nice commuting diagram. And the specific isomorphisms are not too hard either. Essentially, you just take set complements on all of the respective sets. Before I talked about, we have this nice improvement on the lower and upper bounds for BNK. We can actually get corresponding asymptotics on the dual higher Bruhat orders as well. Cool. And so with that, I'll end here. Cool. Thank you.
Thank you so much. Any question for Herman? I do have a question. So, like in the proof, like in the theorem that you said that you have the omega or WP, that you just having the weaving diagram into 0 and 1.
Yeah.
What is the proof of that? Like, how do you see that?
How do we see that like different weaving patterns, like that they capture the commutation classes?
Right.
Yeah. There's a way to kind of an explicit algorithm to recover the reduced expressions. It's sort of an iterative algorithm where you essentially look at the left column, identify a 0 and a 1, and that tells you you have a crossing at the beginning of your diagram. So you can remove the 0 and the 1 to draw your first crossing, delete them, you have to swap the rows, and then you can kind of repeat this process on your weaving pattern, on like a smaller weaving pattern.
I see. I see.
Yeah,
Yeah.
so here you would kind of remove this 0 and a 1, and then you're going to get a 0 and a 1 on the second and third row that you can remove. And each of those pairs corresponds to a crossing in your original weaving diagram, or in your original wiring diagram, sorry.
I see. So, and that works for any, so like the other question that I have is that you start with weak Bruhat order and then have the higher Bruhat order based on the weak Bruhat order. And then, so how about if you use the strong one, even though sometimes it may not be a letters?
Yeah, that's a really good point. So the short answer is I don't think anyone has had a similar generalization. And I've briefly thought about it. I don't quite see a similar way to generalize it. At least in terms of, so one thing I didn't mention is that you can take these maximal chains on the weak Bruhat order, and that will lead to the second higher Bruhat order. Like the maximal chains can correspond to these reduced expressions. Doing the same thing on the strong Bruhat order, I think, just doesn't give you like very nice properties.
I see. Okay.
But I would also be very curious if there is a nice like analog for the strong Bruhat order.
One more question that I have is that at the beginning of your talk, you mentioned that there's like a connection to topology.
Yeah.
So can you briefly explain like how do I see the connection right there?
Yeah, so the original motivation for Manin and Schechtman was they had these hyperplane arrangements that generalized the braid arrangements. And what they were interested in looking at was you look at paths like antipodal points in the chambers in this hyperplane arrangement and look at the order in which you cross the hyperplanes when you draw this path.
Mhm.
And then that's what led to the definition of the higher Bruhat orders is by considering the order in which you cross the hyperplanes. From reading their paper, it seems like they did some work on the topology of these hyperplane arrangements, but it didn't directly like use the higher Bruhat orders. So it's more like they were studying the topology and then noticed that the order in which you cross the hyperplanes was interesting and then put this partial order on it.
I see. So it's more like in the weak Bruhat order instead of on the higher Bruhat order?
Yeah, it's kind of like how in the weak Bruhat order you can consider it as the braid arrangements and then look at the ways in which you cross the hyperplanes. This they generalize that to discriminantal arrangements.
I see. So, but if you generalize the higher Bruhat order back, say for example, that's like this connection between topology and also weak Bruhat order that is known, and then you kind of go up, lift to your higher Bruhat order and go back to the topology. That's something that you don't know how to describe yet.
Yeah, so there is, yeah, I would say when I was talking about the Mobius function, let me scroll back to it. I think maybe I've passed it. Yeah, so this is kind of a topological statement, but which is only true for Bn2, or it's only proven for Bn2, where we look at the order complex of intervals, and it has a very nice, it's either sphere or contractible. There is some topology for the higher Bruhat orders besides this, but it doesn't seem to be as nice. For example, the weak Bruhat order we can also say is exactly like the one skeleton of a polytope, like the permutahedron. But for higher Bruhat orders, I think it's B84. Ziegler and Felsner showed that like it doesn't come from any polytope. So it seems like some of the nicer properties that are true of the weak Bruhat order kind of fail when you go sufficiently far up.
All right, thank you.
Well, thank you.
Any other question?
I have a question if you have anything about enumeration of maximal chains.
Yeah, so the maximal chains, before you do this commutation, before you mod out by commutation equivalence, that gives you the admissible orders, so the ANKs. And although AN2 is known, like this enumeration, AN3 and beyond are also not known, and I don't think they factorize nicely either. So it seems unlikely that there's a product formula for the higher ANKs, but those might be easier to enumerate than BNK, since we don't even know BN2.
And is there any algorithmic results known, like if you need to generate all elements, say, of your BNK in some algorithm, what complexity would it be? Like maybe delay known or something like that?
Yeah, I'm not aware of any like complexity results on generating these sets. But I guess we know that if you actually wanted to count them, it's on the order of like BNK is roughly 2 to the n to the k.
Thank you.
Thanks.
Any other question for the speaker? If not, let's thank the speaker again. Thank you, Herman.